There is an increasing number of applications that benefit from the amount of data acquired by the most affordable and widely available remote sensing sensors. Some of them require processing in real time, and most of them are complex problems requiring high computational power and powerful tools like deep learning models. This requirement makes necessary the use of innovative computational approaches. For example, high-performance computing platforms such as supercomputing, cloud computing, specialized hardware computing, quantum computing, edge computing, even blockchain in remote sensing parallel computation.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring the many ways we can harness the power of artificial intelligence to learn more about our world. I'm also in a personal quest to discover if AI will be more of a help or more of a hindrance to our work as geoscientists. Last episode, we spoke to Dr. Dalton Lunga about how supercomputers are trained. Today, we're flipping the focus to look at how we train scientists to use these incredible high-performance computing structures. This episode of Down to Earth is brought to you by the Geoscience and Remote Sensing Society's technical committees. As part of the world's leading professional association for the advancement of technology, the GRSS technical committees are innovation hubs, bringing together experts from around the world to forward cutting-edge geoscience research, development, and applications. To learn more and be part of the premier community driving the future of geoscience and remote sensing, visit grss-ieee.org and join a technical committee today.
After my PhD, I decided that I wanted to work in applied field. And through one of my colleagues, I discovered that it was very fulfilling to work with remote sensing and Earth observation information because we are solving real-world problems.
This is Dr. Dora Blanco Heras, full professor and senior researcher at CiTIUS at the University of Santiago de Compostela. For 15 years, Dora has been using high-performance and parallel computing to extract knowledge that helps us solve problems related to natural ecosystems.
High-performance computing, parallel computer, supercomputer, cluster computers, and cloud computing basically is an overarching term that describes a category of on-demand computing services. And each computing is a decentralized processing to deliver much higher performance than a typical workstation or a desktop a PC, especially for processing large volumes of data or performing complex calculations.
Dora is the lead for the High Performance and Disruptive Computing Working Group of the IEEE Geoscience and Remote Sensing Society, where she co-organizes the High Performance and Disruptive Computing in Remote Sensing School. This school was started in 2021 as a way of ensuring researchers like you and I could learn about and gain hands-on experience in cutting-edge GeoAI methods and technology. Today, Dora's going to walk us through how the school helps students become familiar with these technologies and how it's boldly wading into future technologies that aren't yet available to the average scientist. So, let's get started. So today, we're talking about high-performance computing, and I always like to ask for definitions before diving into the topic. So can you define high-performance computing for our listeners?
High-performance computing refers in general to the use of supercomputers, big computers, and parallel processing techniques for running advanced applications in an efficient, reliable, and a quick way. It involves, in general, aggregating computing power to deliver much higher performance than a typical workstation or a desktop a PC, especially for processing large volumes of data or performing complex calculations. For example, HPC includes the study of parallel processing, as in many cases, different computers are used in parallel in HPC for solving complex problems. And a parallel computer can be as simple as a CPU, for example, sharing computations with 2 or 3 GPUs, graphical processing units, or can be a cloud infrastructure or an advanced storage infrastructure. In general, computing and storage infrastructures to speed up computations, trying to save time, trying to have a reduced amount of energy consumption, and in general, trying to speed up and make more efficient the computation.
Let's break this down a little bit. What is a supercomputer and how does it differ if we're talking about, say, groups of computer or a cluster setup?
Yeah, we can talk even of a cluster of supercomputers. A cluster is a group of computers working together, splitting the work between the different computers and trying to speed up the computation using these different computers. The case of a supercomputer is a big cluster, including thousands of nodes or thousands of CPUs working in a synchronized way, trying to speed up the computations. Every year, a list of the 500 more powerful supercomputers are published in a top 500 list. We can see this list on the internet. And this list is produced twice per year, analyzing the performance of these machines. At this moment, the most powerful supercomputer is Frontier, a machine that is in the Oak Ridge National Laboratory in the United States. And this list of 500 supercomputers show the number of nodes and the capabilities of all these machines, comparing them based on executing some standard programs.
Yeah, last episode we spoke to Dr. Lunga about Frontier. Pretty incredible, the computing power of these supercomputers. I'm curious. I don't think a lot of people, especially those in the geoscience field, have access to supercomputers. And with the huge amounts of data we have to process for our work, wouldn't it make sense if geoscientists just had access to their own supercomputer?
Well, your question is very related to the content of the school that we usually organize each year. It's necessary to have access to a supercomputer. It depends on your problem. We have different infrastructures and we have to choose the adequate one depending on our problem. In some cases, for example, we need real-time execution. For example, if we are capturing something that is moving, for example, as a result of contamination, and we need to see how petrol is evolving over the sea, it's necessary to have real-time answer to our problem. We need a strong computing capability, but for other problems, it's not necessary to have a real-time answer. So we can organize the computation using more time and a smaller infrastructure. It depends on the problem, and it depends on the amount of data we are processing.
Right, because if you're using a supercomputer and your data is just too small, it's already kind of, say, a waste of the energy and the resources, right?
Yeah.
Okay. I love that you mentioned the HDCRS school, and I'm excited to learn more about it. But first, since today is about supercomputing and AI, I want to ask, what's the relationship between high performance computing and artificial intelligence?
Well, it's important to clarify that we use the words artificial intelligence in a very broad sense. Artificial intelligence encompasses a range of systems, including rule-based systems and cognition, for example, which may not relate directly to remote sensing in the context we are discussing today. Our work is particularly concerned with machine learning models, a part of artificial intelligence, specifically with deep learning models. For instance, we process data from sources like satellites over extended periods of times, for example, a week, to extract correlations between the information. And the deep learning models are trained offline with this data, learning to recognize these patterns. And once the models are trained, these models can perform tasks like segmentation, for example, on new data, because this model has learned how to find the correlations and can find this correlation with new data. So we have a training stage and then what we call an inference stage that is not so heavy computationally from a computational point of view. So this is deep learning. Artificial intelligence means that a system can give a solution to a problem that the system never has found before. It's different. We are only in a particular field of artificial intelligence, deep learning.
Hmm. Thanks so much for differentiating between the general term of AI and deep learning. That's a really important difference to know, especially for scientists who are new to high performance computing. Now, I want to talk about the HDCRS, or High Performance and Disruptive Computing in Remote Sensing School. That's a really long name, but I think it's pretty descriptive. Tell us about this school. Why was it created, and how does it help students and researchers in the field of GeoAI?
Yeah. As the name is a very long name and it's very cryptic. But to start the story from the beginning, the school has the same name as the working group that organized the school. And the working group in GRSS, in the Earth Science Informatics Committee, was created 4 years ago with the objective of promoting the interdisciplinary work in the areas of remote sensing and high performance computing. This working group was proposed for me and Gabriele Cavallaro, a researcher from the University of Iceland, because we have a professional background in high performance computing and remote sensing in both areas. And the first school was organized at the University of Iceland in 2021. And the overall objective of the school is to give participants a comprehensive overview of current topics and methods in the fields of HPC, high performance computing, machine learning, and quantum computing in remote sensing, basically. This is the first objective. And the second one is to establish a venue for students and young professionals to network with senior researchers and professors, leaders in the field of remote sensing, and work on the disciplinary research addressed by the working group. This is basically the goal of the school, to transmit knowledge and to give a platform to exchange experience.
And why do you think scientists, and especially students, graduate students, for example, need this training on high performance and disruptive computing, especially in the field of Earth observation, remote sensing?
Because there is an increasing number of applications that benefit from the amount of data acquired by the most affordable and widely available remote sensing sensors. Some of them require processing in real time, as I said before. And this requirement makes necessary the use of innovative computational approaches that are the focus of the school. The training includes the use of high-performance computing platforms such as clusters or clouds or GPUs, and the topics included in the school are necessary for the students because many of the students know the tools but have a general overview. And we have persons in remote sensing coming from very different fields. Persons coming from ecology, for example, that have only a light knowledge on computing platforms, and they usually access data but don't know how to access data in a more efficient way. They don't know the platforms, the insights of the platforms, how to use them, the available tools, how to access these tools. And this is our objective, give these tools to contribute to obtain better results in a more efficient way and profit of all these platforms, computing platforms and data platforms for accessing data that we have available.
I actually attended the school last year and found the hands-on session on deployable analysis environments really useful. I noticed this year the agenda topics were different. So I'm curious, how do you decide what topics to cover each year?
Well, each year we try to update the school. We are interested in incorporating new platforms because each year we are involved in different projects, know different people, and try to bring to the school the latest. In the working group, we are 4 persons. And each one of us has different expertise. Dr. Rocco Sedona from the Jülich Supercomputing Center, Iskia Gurun from the University of Alabama in Huntsville, and Professor Dr. Sudhaha from the University of Kathmandu. As we all have different contacts and visions, we will incorporate these topics that we find interesting for the next year. We have a common point each year, deep learning models, because it's the state of the art now to use deep learning models. But each year we have to approach the problem from a different perspective. We also incorporate quantum computing, because quantum computing is leading at this moment many of the financial programs, European and at the international level. So this year we included the presentation of a European project working on quantum computing, Penny Lane, that is a powerful tool for researchers and developers exploring the intersection of quantum computing and machine learning, because Penny Lane provides the infrastructure to build, optimize, and deploy machine learning quantum algorithms. So this intersection between quantum computing and deep learning is new this year in the school, because we found these interesting persons that were working in this part, and we are really interested in knowing more about this.
Yeah, last year we learned about quantum machine learning, which, for listeners, is basically using algorithms on quantum computers that are faster than regular computers. It's like the equivalent of giving AI an espresso shot. It's a pretty new area of research, if I'm not mistaken.
Yeah. At this moment, we have small quantum computers, and at this moment, it's important to learn to develop quantum computing algorithms, and we have simulators to simulate these quantum computers, because the technology is evolving very quickly, and it's probably that in the future, we will have quantum computers being coprocessors of a standard computing to solve a particular class of problems for which they are very efficient. One typical problem that can be very efficiently solved by a quantum computer is to decode the password of a person, to find insecurity. If you imagine yourself trying to prove different configurations of a password one by one, we have a big number of possibilities, impossible for you to try all the possibilities. Quantum computing is capable of generating many different solutions at the same time. So it could be very quick to solve these problems. And at this moment, quantum computing algorithms are being developed for almost every task. And it's an experimental topic to apply quantum computing to remote sensing, for example, to deep learning algorithms. And we are very interested in comparing the efficiency and the way of behaving of these quantum computing algorithms comparing to the traditional algorithms. And it's interesting for the remote sensing researchers, because if it's the future for everyone. So it's interesting to know the trends in computation for a HPC student, but also for a researcher in remote sensing.
This was a question last year in our agenda for the HDCRS school. Is Earth observation ready for the quantum computing movement?
Well, this is a very interesting question.
Coming up, we find out the answer to this big question. We also dive into the methods used by the HDCRS school to help prep scientists to use high-performance computing in their own work. Finally, we explore the challenges and opportunities for high-performance computing going forward. All this right after the break.
Want to be at the forefront of geoscience and remote sensing innovation? Then join one of the Geoscience and Remote Sensing Society's technical committees. With 8 committees to choose from, you'll find your niche. From earth science, informatics to data fusion and climate technologies, our committees are driving progress and advancing the state-of-the-art in geoscience remote sensing work. Through our networks, you'll collaborate with global professionals, participate in cutting-edge research, and apply innovations to real-world challenges. Enhance your career, expand your network, and contribute to a better tomorrow. Visit grss-ieee.org and join a technical committee today.
Welcome back. Today we're speaking to Dr. Dora Blanco Heras, full professor and senior researcher at CiTIUS at the University of Santiago de Compostela, and lead of the HDCRS working group, which organizes the yearly High Performance and Disruptive Computing in Remote Sensing School. As you heard during the interview, I attended this summer school last year, and it was an incredibly useful space to learn from leading scientists in the field of high-performance computing. What I appreciated the most was the way students gained both theoretical as well as hands-on learning. Most importantly, the school features sessions on topics that are at the cutting edge of GeoAI, like quantum computing. Do you think Earth observation is ready for the quantum computing movement? Let's find out what Dora had to say.
Nobody is ready for the quantum computing movement. It's very interesting because it's an open issue. We have to learn, we have to work more, but it's interesting to be the first one to try these algorithms, to have a conversation with these researchers that are leading this research. And it's very interesting to ask them, please explain me. It's the same to use a quantum computing algorithm than my traditional algorithm. How can I improve? What's the future? The day when we were talking about quantum computing, I talked to these researchers, explain me, a quantum computer will replace a standard computer in the future? The answer is probably not. Nobody knows the answer, but they will be perfectly coprocessors to send them some computations. So it's the future. It's difficult to predict.
So basically, it's just still exploratory, and also we'll see how technology goes in the future. It's fast,
Yeah.
Well, it's pretty exciting that we're getting premier access to these kinds of sessions. Now, based on my experience, the school combines theory and hands-on practice to teach students new concepts. So, can you tell us more about how this works? Why is this a good way for training people on high-performance computing methods?
Yeah, we thought since the beginning that it's interesting to offer not only theoretical presentations, we need hands-on sessions to give an approach to the problem. This is the reason of having a limited number of students for our school. We have 30 students at a maximum because for these hands-on sessions, we need to be in contact with the students. The persons who are in the session need to answer questions to the students, to interact with them. And we have different approaches, but a common approach is to use a Jupyter notebook that is an easy way of helping the student to build with the teachers a solution or an algorithm using a computing platform. And usually a presentation is offered, and then the teacher says, well, open this Jupyter notebook. You can add the information using these sentences or these structures and see how the results are represented. Or for example, we have a foundation model. What is a foundation model? Then I access the foundation model, and I know how to adapt, fine-tune this foundation model to our problem. This is basically the structure of the hands-on that we usually develop here.
For me personally, having the hands-on learning was a really useful way of applying the theoretical presentations that were provided to us. And it makes it easier to remember and also understand the concepts.
Yeah.
And just out of curiosity, the school is called High Performance and Disruptive Computing in Remote Sensing. When you use the term disruptive computing, what does it mean?
Disruptive computing, this name was invented by me and Professor Gabriel Cavallaro because we wanted to include edge computing. It's not high-performance computing. We don't have thousands of nodes, but it's related to innovative ways of computing. This is disruptive computing. Edge computing, quantum computing, the use of GPUs, the use of FPGAs, blockchain is disruptive computing. These innovative ways of computing that do not require necessarily a supercomputer or a very expensive computer.
Right. I just I was just thinking how the term disruptive is also like every day in our lives. Like, for example, disruptive services, like how Uber was created because we had the need to find a simpler way to actually access a taxi going from one place to another, something like that, isn't it?
Yeah, it's something like that, because when we are driving a car, we are not aware of the number of units of computation, of chips computing, making computation that are in the car. For example, for different parts of the car, we have different sensors making computations. And this is a disruptive computation, is a computation related with Internet of Things, is a computation very small. We have very small devices with only a couple of tasks to be performed, but very efficiently. And the cost is less than $1, only some pences, but it's enough for this task.
So it completes the whole.
Yeah.
What challenges still exist when it comes to high performance computing?
Well, this is a very interesting question, because high performance computing faces continuous challenges as the computing infrastructure are of increasing size and capabilities. This is in part a consequence of the evolution of integrated circuits, but it's a consequence that more complex problems require innovative solutions. And we have, for example, in remote sensing, many sensors, and we have more and more information available. And we try to solve problems that are big this year than the year before. Scalability and performance are key issues in high performance computing. What is called exascale computing, achieving a performance of millions of flops, of floating operations per second. Obtaining more and more performance is a significant challenge. And this requires advances in hardware, in software, in energy efficiency. We require more research in parallelism. As HPC systems grow, efficiently managing and scaling parallelism across millions of cores of nodes becomes increasingly complex. Energy efficiency is also very interesting for all of us, reducing power consumption in these machines, making more efficient cooling systems, heterogeneous architectures, for example, integration of different technologies. Modern HPC systems integrate a variety of processors, CPUs, GPUs, FPGAs. This requires sophisticated software frameworks to optimize the workload across these heterogeneous architectures. New programming models, data management and storage, big data integration, for example, data movement, minimizing the limitation produced by the data movement between different machines. Security, for example, and privacy are key issues in high performance computing. Software development, quantum computing integration is also an issue. And very important for the school, democratizing access, making HPC resources more accessible to a broader range of users, including smaller research institutions and industries. Developing user-friendly interfaces, for example, is an open issue. Simplifying the user interfaces and programming environments to make HPC more approachable for non-experts.
I love that focus on democratizing access to HPC resources. That's really important for GeoAI moving forward, especially if we want to make sure AI in the geosciences remains useful and ethical, which brings me to my last question. Dora, this season, we're exploring whether or not AI will be more of a help or a hindrance in geoscience and remote sensing work. What are your thoughts on this?
This has a relationship with my first answer related to artificial intelligence. If we think artificial intelligence are like a monster that is observing us and making decisions instead of us, this is a very huge problem. But deep learning algorithms are very inoffensive. We are learning a mathematical model called deep learning model to extract knowledge and correlations between Earth observation data, trying to extract information, and I decide how to use this information. For example, we are detecting invasive species in our river sites. If I detect an invasive species, I raise an alarm. I decide when to raise an alarm from information offered by the deep learning algorithm, but I have reference information to contrast this information. I'm not giving permissions to the deep learning model to make anything. In remote sensing, we are extracting relationships representing the information in a different space, trying to extract the relevant information that is not easy to observe with our eyes or with other tools, but we decide how to do with information. It's not taking shares of our lives or our information. Artificial intelligence in that sense is different. It's related probably with cognitive systems or to other fields of artificial intelligence, but it's not the problem in remote sensing at this moment, as we are using very inoffensive tools.
Education is a fundamental driver of growth and progress, yet access to this vital resource remains uneven across the world. In the rapidly evolving field of AI, having the opportunity to learn about current trends and understand the limitations and potentials of this technology is crucial. Without access to this knowledge, individuals and communities are at risk of being left behind, which can contribute to uneven power dynamics globally. This will be a disservice to development of AI technologies and could even be dangerous. However, I strongly believe that learning AI in environments like the HDCRS school empowers individuals not only to understand AI, but to actively contribute to shaping its future. When people are given the tools to grasp both the capabilities and limitations of AI, they are better equipped to ensure that it serves as a force for good. And I can affirm that this AI can be of help. In our next episode, we're diving into the exciting world of foundation models. While you wait for that episode to come out, go and learn more about Dr. Dora Blanco Heras' work by connecting with her at CiTIUS.gal, that's CiTIUS.gal. You can also learn more and even get involved with the High Performance and Disruptive Computing in Remote Sensing School or Working Group by visiting hdc-rs.com. Be sure to follow and rate us on Spotify and Apple Podcasts, and check out our sponsors by following them at IEEE_GRSS on X and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Killa Media. And a special thanks to Manil Maski and Fabio Pacifici for their support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.